Welcome to the Deep Dive, the show where we take that fire hose of information you share with us and really try to distill it down, get to the pure, powerful insights you need to understand the world.
Yeah, and today, look, we're wading into probably the most polarizing subject out there right now, artificial intelligence.
It really feels like every single day there's a new headline, doesn't it? It's either promising, utopia or predicting immediate collapse. It's quite overwhelming.
It is.
Yep.
That's absolutely right. And if you only listen to those headlines, I mean, you'd think AI is either this, like general intelligence arriving tomorrow to solve everything,
Right. Cure cancer and poverty.
or it's some rogue entity, currently plotting our swift extinction in a basement somewhere.
So our core mission today is really to cut through all that noise, that hyperbolic stuff, and just do a clear, objective analysis.
Exactly. We are focusing squarely on the places where machine learning has actually achieved um, undeniable, measurable, and importantly, repeatable success.
Yeah. We're not looking for AGI today. Forget the science fiction for a moment. We're looking for high utility specific intelligence. The areas where the tech has already genuinely transformed major industries. And we want to contrast that sharply with the domains that are still, frankly, science fiction or maybe just high risk speculation.
Right. And for you, the listener, the goal really is to leave this dive with a much clearer understanding of what AI is actually good at right now in the real world.
And you have this unifying theory, this thread that connects all these success stories.
Well, yeah, the way I see it and the way the research suggests is that the current generation of successful AI, it's fundamentally a prediction machine.
A prediction machine.
Okay.
Not thinking, but predicting.
Exactly. It's not reasoning in the human sense.
Mm-hmm.
It's making prediction incredibly cheap, incredibly fast, and scalable. And that radically changes the economics of decision-making all over the globe.
Okay, so cheap prediction is the golden thread we're going to follow.
That's the plan.
We'll look at four main areas where this cheap prediction power really yields tangible results. So first, how pattern recognition is changing medicine.
Then how optimization is saving, well, billions in global logistics and infrastructure.
Third, the role of rapid financial security, specifically things like fraud detection.
And finally, the huge augmentation happening now thanks to the natural language processing breakthroughs we've all been seeing.
All right, let's unpack this. That crucial difference between the hype and the reality. Where does AI actually work? So when AI looks at the world, its first, maybe its most celebrated superpower is recognizing incredibly complex patterns, especially in visual data, right? Images, videos.
Absolutely. And the technological backbone for this revolution, the thing that really kicked off this modern AI boom we're in, it's something called a convolutional neural network, a CNN.
CNNs, I've heard the term, but what makes them so special for images?
Well, CNNs are probably one of the most remarkable examples of us trying to reverse engineer biology and computing.
Really? How so?
Their whole design philosophy, it's directly inspired by the structure of the visual cortex in our own brains. It's like a literal attempt to mimic how we process images, but doing it in silicon.
That biological link is fascinating. Can you break that down a bit? How does a CNN actually mimic how our eyes and brain work together?
Sure. Think about how you see something. Your visual cortex, it works hierarchically, in layers. It uses lots and lots of specialized neurons that only process information from tiny, restricted subregions of what you're seeing.
Like little windows.
Exactly, little windows. Scientists call them receptive fields. And these fields, they aren't trying to recognize a whole cat or a car right away. They're responsible for identifying the most basic features first.
Basic features like?
Things like specific angles, maybe a vertical line here, a horizontal edge there, certain patches of color or gradients, really simple stuff.
Okay, so if I'm looking at a picture, say, of a cat, the first layer of the network, or the first part of my brain dealing with it, just sees a curve, a patch of fur texture.
Precisely. That's layer one. Then the subsequent layers, think of them as higher level processing. Like in our neocortex, they take those basic outputs, those lines and curves, and they start stitching them together hierarchically.
Building up complexity.
Right. They might combine two lines to recognize a corner, then combine several corners and edges to see a distinct shape, like an ear. And eventually, this builds up into a complex understanding of the whole scene that lets us recognize, that's a cat, or that's a bicycle, or maybe even spot a tumor in an X-ray.
And CNNs replicate this layered process.
They do. They use specific types of layers, convolution layers, to act like those feature detectors, nonlinearity layers, pooling layers to sort of generalize. and they're trained using supervised learning on absolutely immense data sets to identify objects through that same kind of hierarchical feature building process.
You mentioned immense data sets, and I know when we talk about proving the power of CNNs, the big breakthrough was ImageNet. The scale of creating that, it's hard to wrap your head around.
Oh, it was just monumental. And it's really critical to remember this. This seemingly autonomous machine learning success, it was powered by massive, painstaking human labor.
Right, the labeling.
The sheer volume of accurate labeling was the secret sauce. The ImageNet dataset, it was created by pooling the work of something like 49,000 workers, people from 167 different countries.
Wow.
Over 2.5 years, these people meticulously labeled 3.2 million high-resolution images, identifying objects, drawing bounding boxes.
That sounds like an enormous amount of what some people call ghost work, doesn't it?
Right?
Powering this huge technological revolution behind the scenes.
It really does. And it just speaks volumes about the fundamental value of high-quality, ground-truth data in making these systems work. You can't just have algorithms. You need the data.
Then the payoff was huge.
Undeniable. That huge, accurately labeled data set, it became the international benchmark, the gold standard for researchers everywhere.
And having that common goal, that massive testbed, it just accelerated progress.
Massively. It allowed researchers to push image recognition algorithms so far that now, in certain very specific visual domains, some AIs can actually recognize images with superhuman accuracy. Better than the average person, sometimes even better than experts in narrow fields.
Okay, so CNNs were key with that built-in biological inspiration, that idea that nearby pixels matter. But things evolve, right? Newer models like vision transformers or VITs are becoming more dominant now.
That's right. Technology never stands still.
What's the fundamental difference in how a VIT sees the world compared to a CNN?
The key difference lies in something called inductive bias.
Inductive bias, meaning?
Meaning the assumptions built into the model's architecture. A CNN has a lot of built-in inductive bias because of its structure. Those convolutional filters inherently assume that spatial locality matters, that nearby pixels are related. That reflects the biology we just talked about.
Okay, that makes sense.
The newer vision transformers, VITs, they have much less of that inherent bias. They don't automatically assume nearby pixels are special. Instead, they treat an image almost like a sentence.
Like a sentence? How?
They break the image down into a sequence of fixed-size patches, and then they use this powerful mechanism called self-attention, which was actually borrowed from the world of natural language processing, from models like the transformer that powers ChatGPT.
Attention,
Yeah.
allowing it to weigh the importance of different parts of the image relative to each other, regardless of where they are.
Exactly. It looks at all the patches simultaneously and decides which ones are most relevant to understanding any given patch.
So if they don't have that built-in assumption about nearby things being related, how do they get such good results? Sometimes even better than CNNs.
Basically, they substitute architectural bias for sheer scale.
Scale of data.
Scale of data. Because they lack that inherent structural trick, that spatial assumption, VITs require training on extraordinarily large data sets to perform well. We're talking data sets like ImageNet 21K or Google's internal JFT300M, which contain orders of magnitude more images than the original ImageNet that CNNs cut their teeth on.
So it's brute force data overcoming the lack of built-in assumptions.
In a way, yes. The sheer volume of data allows the model to learn those spatial relationships implicitly, rather than having them hardwired in the architecture. It's the power of massive data sets enabling these less biased architectures to learn effectively.
That's a really fascinating trade-off. Clever, biologically inspired design versus just raw data scale.
Right.
Okay, so let's pivot to maybe the most life-altering application of this pattern recognition power. Medicine.
Yeah.
And we're not talking science fiction robot surgeons here, are we? We're talking about AI augmenting diagnosis today in fields like radiology, pathology, dermatology.
Precisely. This is where AI starts to move beyond what you might call the binary world of traditional medical data interpretation.
The binary world, you mean like normal or abnormal?
Exactly. Historically, your lab results say your cholesterol level, your blood pressure, your hemoglobin count, they get measured against population averages.
Yeah.
Huge statistical ranges. And the report just gives you a simple normal or abnormal based on where you fall within what's typical for millions of other people.
But that average patient doesn't really exist, right? We're all individuals with our own baselines.
That's the crucial insight. And relying only on those broad population averages, well, it can lead to critical misdiagnoses because the busy human doctor is often just glancing at that normal flag, relying on a statistical range derived from a huge, diverse population, not necessarily what's normal or changing for that specific individual over time.
So how does AI fix this? Can you walk us through a concrete example, like that hemoglobin case you mentioned?
Certainly. This really gets to the core of a concept some researchers call augmented individualized medical support, or AIMS. So imagine a busy doctor reviewing a patient's latest lab work. The doctor sees the patient's hemoglobin level is, say, 13.2 grams per deciliter. The lab report clearly marks that number as normal, based on the standard population range.
So no red flag. The doctor moves on to the next patient or the next data point. Makes perfect sense in a busy clinic.
Seems logical. But the AI, which has access to the full patient history, sees something else. It tracks that same patient's hemoglobin steadily declining over the last 5 years. Maybe it started at 15.9, then dropped to 15.0, then 14.2, and now it's at 13.2 GDL.
Ah, so all those numbers might still be within the official normal range.
Correct. Every single one of those readings could be comfortably within the wide population-based normal limits. But the trend itself, that consistent downward trajectory, that's the crucial signal the AI picks up on.
The chronic decrement over time is telling a story that the single normal data point completely hides.
Exactly. That chronic decrement, even if it stays within those population bounds, could be a very early warning sign. It might indicate an underlying disease process like hidden gastrointestinal bleeding, maybe an early-stage cancer, or some other chronic inflammatory condition that's slowly developing.
And the AI can flag that trend as unusual for this specific patient.
Precisely. By processing that rich, granular, continuous data for that individual, the AI can flag that steady decline as highly unusual for that patient's own baseline, providing a personalized intervention alert that the population averages would completely mask.
That's a fundamental shift, isn't it? Moving from just population health statistics to truly personalized health monitoring.
It really is. It's augmenting the doctor, not replacing them, by finding subtle patterns in individual longitudinal data that are almost impossible for a human to track reliably across thousands of patients. Hashtag #TakeTack22. Success in optimization and logistics.
That's a genuinely revolutionary application in healthcare. Okay, let's shift gears. Moving from the human body to, say, the global corporate infrastructure. How does this idea of cheap prediction translate into massive, measurable economic value there?
Well, the core economic driver again comes back to that idea of reducing uncertainty.
Uncertainty, that's always the big unknown in business, isn't it?
Historically, it's been the primary source of friction, of cost, in the global economic machine. Businesses spend fortunes hedging against uncertainty, they hire armies of people just to try and predict it, and they still lose vast amounts of money because of unexpected events.
Right. Supply chain disruptions, demand fluctuations.
Exactly. So when AI comes along and makes prediction cheap, whether it's predicting future customer demand much more accurately, or optimizing traffic flow in real time, or predicting when a critical machine part is likely to fail, it fundamentally reduces that uncertainty baked into decision-making.
And less uncertainty means?
It means less waste, better resource allocation, smoother operations. It generates tremendous economic value, sometimes almost instantaneously.
And you mentioned this reduction in uncertainty is actually so profound, it even impacts really high-level corporate strategy, like how firms decide what to do themselves versus what to contract out, the classic boundaries of the firm idea.
Yes, this is a really interesting application of Nobel laureate Ronald Coase's theory of the firm, but sort of updated for the AI age. Coase talked about transaction costs determining firm boundaries.
Right, the costs of coordinating things in the market versus inside the company?
Well, prediction reduces those transaction costs. When prediction becomes cheap and reliable, it actually increases a company's incentive to contract out tasks that are heavily focused on data analysis, prediction, and structured actions based on those predictions.
Why? Because it's easier to check their work.
Exactly. Because those tasks are now much easier to specify clearly in a contract, and you can monitor the external provider's performance much more effectively using AI-driven metrics. Think about outsourcing demand forecasting or maybe road optimization.
Okay, so if I need someone to predict my future stock levels or optimize my delivery routes, I can hire an external AI specialist firm and feel pretty confident I can track whether they're delivering the goods, literally.
Precisely. But, and this is the critical distinction, this same cheap prediction decreases the incentive for firms to contract out tasks that require complex, hard-to-define human judgment.
Ah, okay. Why is that? Because judgment is the squishy stuff, the part that's hard to automate or even write down.
You've got it. You can't easily write a contract that precisely specifies the required quality of, say, human strategic vision, or complex negotiation skills, or really novel problem solving. And you certainly can't reliably monitor that kind of nuanced judgment from the outside.
So as AI handles the predictable stuff,
The human judgment part becomes even more valuable, relatively speaking. And since prediction machines reduce the uncertainty surrounding all the other parts of the business, the data, the logistics, the likely outcomes, these core judgment and innovation roles become the key differentiators for human labor within the firm.
so firms are more likely to keep those crucial judgment roles in-house, where they can manage and nurture that high-value human expertise directly.
That seems to be the trend, yes. AI handles the prediction, humans handle the judgment and the exceptions.
Okay, let's get concrete. For a really fantastic, large-scale, real-world example of prediction-driving automation and efficiency, you pointed us towards the world of mining, specifically Rio Tinto in Australia's Pilbara region.
Yes, this is probably the definitive global case study right now in large-scale logistics optimization through AI. Rio Tinto deployed this huge autonomous fleet. I think it was 73 self-driving haul trucks.
And these aren't like little trucks.
Oh no, these things are the size of two-story houses. Massive machines, hauling iron ore out of these enormous open pit mines, more than 1,000 miles from the nearest major city. It's incredibly remote.
So you've got this whole ecosystem of giant synchronized robot trucks operating in one of the world's harshest, most remote environments. What are the actual measurable benefits AI brought there? How did it make this possible?
Well, the real sophistication of the AI isn't just driving the truck straight. It lies in its ability to constantly predict a whole range of dynamic variables in real time.
Like what?
Predicting potential hazards on the haul roads, predicting the optimal sequence for trucks to arrive at the shovels and the crushers, and coordinating the minute-by-minute traffic flow of all 73 of these behemoth vehicles navigating into and out of these deep, winding pits without colliding or causing traffic jams.
That level of coordination must be incredible.
It is. And it's what allowed them to achieve full autonomy and really maximize the throughput, the amount of ore they could move.
And the bottom line, the economic results.
The numbers are pretty staggering. Rio Tinto reported that this automation saved them about 15% in operating costs.
15% is huge in an operation that size.
It's massive. And a big reason why is the utilization. The mine now runs these trucks 24 hours a day, 7 days a week, 365 days a year.
No breaks needed.
No mandatory rest breaks for drivers, obviously. No driver-related safety incidents or requirements inside the cab. No need for air conditioning in the cabs, which is a non-trivial cost in the Pilbara heat.
And you mentioned something about turning around.
Right. Critically, the optimized routing and the autonomous nature means they could design routes that minimize or even eliminate the need for these huge trucks to perform slow, complex turnarounds in tight spaces within the pit. That saves time, reduces wear and tear, improves safety, and increases speed. AI essentially eliminated all that unpredictable human downtime and dramatically optimized the physical flow of material.
That's efficiency on a grand scale. And beyond just moving physical stuff like ore, we see this optimization power applied to managing core infrastructure too, right? Like data centers.
Absolutely. Think about the giant data centers that power the internet. They're constantly fighting this thermodynamic battle just to stay cool. Cooling is actually one of the single largest operating expenses for companies like Google or Meta or Amazon.
I can imagine. All those servers generate immense heat.
Exactly. So DeepMind, which is Google's AI research lab, leveraged reinforcement learning and prediction algorithms, predicting things like future temperatures, server loads, optimal fan speeds, and they deployed systems that managed the cooling infrastructure in Google's data centers.
And the result?
They reported reducing the cooling energy consumption by an impressive 40%.
40%. Across Google's global footprint of data centers, that must be colossal savings.
Colossal, both in terms of cost and environmental impact. It's a huge efficiency gain driven purely by better prediction and control.
Okay, let's transition to a financial success story. One that probably impacts almost every single one of us listening. Fraud detection.
Ah, yes. This is perhaps the purest, most ubiquitous prediction application out there.
Why do you say purest?
Because fraud detection is inherently a high-volume, repetitive prediction task. The system takes input data for, say, a credit card transaction, the amount, the location, the time of day, the user's past history, the merchant type, etc.
Lots of data points.
Lots of data points. And it combines all that with a machine learning model to predict a very specific, usually binary risk outcome. Is this particular transaction likely fraudulent or is it legitimate?
And it has to do it instantly.
Instantly. millions of times a second globally. It's the perfect task for supervised machine learning because the ground truth, was it actually fraudulent, is actually revealed when the customer reports it or doesn't. That feedback allows the model to continuously learn and improve its predictions over time.
It's a huge success story for AI. But while AI is great at augmenting many tasks, this specific success in white-collar automation, like fraud detection or underwriting, it does highlight a potentially challenging trend for some jobs, doesn't it? Professions that rely heavily on that kind of routine processing and prediction.
That's a necessary observation, absolutely. When prediction becomes automated and cheap, the people whose primary job function was performing those routine predictions, well, they inevitably face displacement or significant changes in their role.
Like the insurance underwriters you mentioned.
Exactly. The rise of automated underwriting software is a prime example. This software uses AI to predict the risk associated with an insurance policy or a loan application far faster and often more accurately based on data patterns than a human could. This allows the remaining human workers to process applications much, much faster, focusing maybe more on complex cases or customer interaction.
But it means fewer underwriters are needed overall, and the numbers actually bear this out quite dramatically, don't they?
They do. The U.S. Bureau of Labor Statistics, for instance, projected a pretty significant decline. I think it was around 13% in the per capita employment of insurance underwriters just between 2016 and 2026.
Wow, 13% decline in a decade?
Yeah. And that's not just theory. It's a measurable consequence of this successful targeted prediction technology rapidly displacing or reshaping roles that were primarily defined by routine data processing and risk assessment based on established rules and historical data. ##3, transformation through natural language processing, NLP.
Okay, so we've covered images and optimization. Let's move to the third domain of, well, undeniable AI success. The realm of language. This is brought to us mostly by the large language models, the LLMs, that have just completely captured the world's imagination recently.
Yeah, ChatGPT, Claude, Gemini.
Uh-huh.
These are the generative engines we're all interacting with daily now.
And their success is truly remarkable. It feels like it came out of nowhere almost. What was the key technical breakthrough that enabled this leap in language ability?
It really hinges almost entirely on a specific technical innovation that came out of Google research back in 2017. The transformer
The
architecture.
transformer, okay. Before the transformer, what were language models like? What were they using?
Before transformers, the dominant approaches relied heavily on something called recurrent neural networks, or RNNs, and variations like LSTMs, long short-term memory networks.
And what was the main limitation of those older RNNs that the transformer managed to solve?
Well, RNNs process text sequentially, word by word, one after another, like reading a sentence from left to right.
That sounds intuitive. What's the problem with that?
It created two major bottlenecks. First, because they processed sequentially, they couldn't be easily trained using parallel computing across multiple processors, which really limited how large and complex the models could become. Training took forever,
Okay, so a scaling
a
problem.
big scaling problem. And second, maybe even more critically, they suffered from what's called the vanishing gradient problem.
Vanishing gradient.
Yeah, essentially it means they struggle to maintain memory or capture dependencies across long stretches of text. By the time an RNN reached the end of a long sentence or a paragraph, it had often effectively forgotten the crucial context established way back at the beginning. It couldn't easily link pronouns back to nouns mentioned paragraphs earlier, for example.
So long-range context was the killer.
It was a major limitation. So the transformer architecture fundamentally changed the game by introducing this mechanism we touched on earlier with vivites, the attention mechanism.
Right? Attention, allowing it to look across the whole text at once.
Precisely. The transformer architecture really relies on two key components working together brilliantly. First, that attention mechanism. Functionally, attention allows the model, for every word it's processing or generating, to look back and forward across the entire input sequence simultaneously and weigh the importance of all other words.
Can you give us an analogy for how that helps understand context?
Sure, think of it like you're reading a complex sentence, maybe something like, "The bank robber arrived at the riverbank."
Okay, two meanings of bank.
Right. An RNN might struggle.
Ah.
But the attention mechanism allows the model, when it sees the second bank, to instantly look back at river and robber and figure out, based on river, this bank means the edge of the water, not the financial institution. It calculates relevant scores between all the words.
So it can dynamically decide which parts of the context matter most for interpreting each specific word, no matter how far apart they are.
Exactly. It gathers all the necessary context globally across the text. That's the first key piece.
And what's the second component you mentioned? The feed-forward networks.
Right. The feed-forward networks, FFNs. After the attention mechanism has done its job of mixing information and figuring out which words are relevant to which other words, creating this sort of rich soup of contextual information for each word,
Okay.
the FFNs come in. These are basically layers of standard, relatively small neural networks that are applied independently to each word's representation in the sequence. They introduce crucial nonlinearity, the ability to learn complex relationships, and they act as a processing unit.
So they take that contextual soup from attention.
And they transform it. They process it, refine it, and turn it into useful, higher-level features that the model can then use in the final step, predicting the next most likely word or token in the sequence.
And it's this combination, attention for context, FFNs for processing, that somehow allows these models to learn the incredibly complex, nested, almost tree-like structure of grammar and syntax that's inherent in human languages.
That's the magic, yes. It turns out this architecture is remarkably effective at capturing those long-range dependencies and hierarchical structures, which is why LLMs can generate such coherent, grammatically correct, and often contextually relevant text.
Amazing. Okay, so let's look at a really hopeful application of this powerful language capability. Education. Many experts are pointing to generative AI, saying it holds the potential to finally solve what's sometimes called the holy grail of learning.
I mean, the need for universal, high-quality, individualized tutoring.
Exactly. The potential impact here feels enormous, maybe even truly equitable if done right.
I agree. Imagine an AI tutor, a virtual teacher, that isn't just, reciting facts from a textbook or grading multiple choice questions. Imagine one that's paying constant specialized attention to each individual learner.
More than just tracking right or wrong answers, it must be tracking how the student is actually learning moment by moment.
That's the key. Using potentially integrated pattern recognition, maybe analyzing facial expressions via camera, tracking eye movement, looking at hesitation times and responses, it can notice subtle cues.
Like,
Are the student's pupils dilating, indicating engagement or cognitive load? Are their eyelids drooping, suggesting boredom or fatigue? Is the pace of their typing or mouse movements changing?
and the AI could use these signals.
To deduce exactly what teaching cadence, what tone of voice, what specific type of analogy or explanation makes that particular student learn fastest and stay most engaged. Even if that specific teaching method completely fails for thousands of other students, it can tailor itself to the individual.
And the natural language processing part allows for incredible customization of the actual learning material itself, too.
Absolutely. If the system detects that a student has a really high interest in, say, basketball or maybe ancient mythology,
Yeah.
the LLM can dynamically rewrite complex, abstract math problems or physics principles into a narrative or context focused specifically on that preferred domain, making it instantly more relatable and engaging.
So instead of a generic word problem about trains, it's about calculating LeBron's shooting trajectory or something.
Potentially, yes. This hyper-customization, tailoring both the delivery and the content, dramatically improves engagement and, theoretically, learning speed. And this level of continuous, personalized, adaptive attention and customized content. This is precisely what holds the potential to finally address Bloom's 2 sigma problem.
Okay, Bloom's 2 sigma problem. Remind us what that is and why the AI tutor is seen as a potential solution.
Right. So Benjamin Bloom was an educational psychologist whose famous 1984 study showed something remarkable. He found that the average student who received one-on-one human tutoring performed 2 standard deviations better than students who learned the same material in a conventional classroom setting.
2 standard deviations. That's a massive difference, right? That's like taking an average student at the 50th percentile and boosting them up to the 98th percentile.
Exactly. It's a gigantic improvement in learning outcomes. The problem for the last 4 decades has been that providing high-quality one-on-one human tutoring is just incredibly expensive and resource-intensive. It's economically impossible to scale universally to every student.
The ultimate educational inequality, in a sense.
Right. But now, generative AI, through platforms like Khan Academy's Khanmigo TutorBot, for example, offers potentially the first truly scalable path to provide that kind of high-quality, interactive, mastery-based tutoring universally, focusing on ensuring the student achieves full comprehension at their own pace before moving on.
That is genuinely an amazing potential triumph for education globally. But as with all these technologies, every machine learning success seems to have its Achilles heel. And for LLMs, that weakness is the infamous problem of hallucinations.
Ah, yes. The tendency to make things up.
And this isn't just a random error, is it? You argue it fundamentally exposes the core limitation of these sophisticated pattern matching machines.
I think that's the critical takeaway here, yes. Hallucinations, when an LLM generates plausible, grammatically perfect, often highly confident sounding, but factually false information, they are some weird aberration or a bug that can be easily fixed.
They're a feature, not a bug.
In a fundamental sense, yes. They are a necessary feature or consequence of the underlying probabilistic pattern matching mechanics. Remember, the neural network is primarily trained to predict the next most likely word or token based on the patterns in its vast training data.
So its main goal is to sound convincing and fluent, to match the patterns of human language it learned. Factual accuracy is secondary.
Often, yes. Factual accuracy is just one pattern among many. The model prioritizes generating text that fits the statistical patterns of its training data text, that sounds plausible, that flows well, that uses the right kind of jargon for the context. If generating a completely bogus legal decision, complete with fake citations, fits the expected pattern of legal discourse better than pausing and saying, "I don't know," the model is often biased towards generating the plausible lie.
Because I don't know might be statistically less common in its training data for that kind of prompt.
Exactly. And we saw this limitation exposed in a really high-profile, almost comical way in the legal field not long ago, didn't we?
Yes, that case made headlines everywhere. Tell us about it.
Right, there was a lawyer in New York, I believe, who used a generative AI, likely ChatGPT, to help with legal research and prepare arguments for a court filing.
Okay, seems like a plausible use case.
Seems plausible, except he subsequently submitted these filings to the court. And the opposing counsel, and then the judge, realized that several of the case precedents cited in the brief simply didn't exist.
They were completely made up.
Entirely fabricated by the AI.
Yeah.
The judge's ruling sanctioning the lawyer mentioned bogus judicial decisions, with bogus quotes and bogus internal citations. The AI had just confabulated sources that sounded perfectly real but were pure fiction.
Wow, that perfectly illustrates the point, doesn't it? The AI is incredibly good at synthesizing text that looks and sounds right based on statistical patterns.
But it has absolutely no inherent mechanism for ensuring factual knowledge, truthfulness, or any kind of real semantic understanding of the concepts it's manipulating. It's just predicting the next most plausible token.
Okay, so that stark failure, the ability to be incredibly fluent yet simultaneously untruthful, it brings us right to the core philosophical lesson we need to draw from AI's current successes and failures. There seems to be this monumental difference between being good at prediction based on patterns and actually having a working model of the world.
That's exactly right.
What is the human brain doing fundamentally that current AI systems, even the best ones, are still missing?
Well, current AI, whether it's a CNN looking at pixels or an LLM looking at words, primarily excels at one thing: predicting the next input, the next likely pixel value, the next likely word, the next likely transaction outcome, all based on identifying statistical patterns in massive arrays of numbers derived from training data.
It's pattern matching and sequence completion, essentially.
At its core, yes. In stark contrast, the human brain, particularly the neocortex, does something fundamentally different. It learns and continuously refines a rich, detailed, structured model of the world and everything in it.
A model of the world, not just patterns and data.
Right. And this model isn't just a flat collection of facts. It's highly structured, often organized by what neuroscientists like Jeff Hawkins call reference frames.
Reference frames, what does that mean?
It means our brain understands objects and concepts in relation to each other, and crucially, in relation to our own body. A fundamental unit in the neocortex needs to know the location of its sensory input relative to the object being sensed and relative to our own body's position and orientation in space.
So my brain doesn't just know cup. It knows cup is on the table is in the room is here relative to me. If I reach out my hand this way, I'll touch the cup.
Exactly. It's a self-referential, sensory-grounded, compositional model. And this rich world model isn't just passive. We use it constantly, moment by moment, to predict what our next sensory input should be, especially as we move and interact with the world. We're constantly checking our predictions against reality.
So when I interact with something complex like a bicycle, I don't just recall a list of statistical associations about the word bicycle. My brain activates this multi-dimensional model.
Right. A model that includes the parts, wheels, pedals, handlebars, how they're arranged spatially relative to each other, how they move together causally, what sensations I should expect when I push the pedal or turn the handlebars. It's grounded in physics and experience.
And that grounded, causal, compositional model of the world, that's the key element you're saying is missing from current AI, which operates mostly on abstract symbols and vast arrays of numbers without that inherent physical grounding or spatial causal structure.
That seems to be the fundamental difference, yes. Current AI lacks that deep, intuitive, experience-based understanding of how the world actually works.
This limitation, this gap between symbolic manipulation and real understanding, it sounds an awful lot like a classic philosophical objection to the very possibility of machine intelligence. John Searle's Chinese room argument.
It maps onto it perfectly. The Chinese room thought experiment is ideal for reinforcing this boundary between mere computation manipulating symbols according to rules and genuine comprehension or semantics.
Can you quickly walk us through that analogy again and connect it to this idea of syntax versus semantics, maybe weak versus strong AI?
Sure. Searle asks you to imagine yourself as the operator locked inside a room. You don't understand a word of Chinese. Inside the room, you're given baskets full of Chinese symbols, which you can't read. You're also given a huge, complex rule book, written entirely in English, a language you do understand.
So the rule book is like the computer program.
Exactly. It's the algorithm. The rules might say things like, if you receive a symbol that looks like squiggle squiggle, followed by a symbol that looks like triangle square, then find the symbol that looks like squoggle squoggle in another basket and pass that one out under the door.
You're just matching shapes based on the English instructions. Purely syntactic manipulation.
Purely syntactic. Unbeknownst to you, the symbols being passed into the room are called questions in Chinese, and the symbols you are meticulously passing back out, following the rules, are perfectly coherent answers in Chinese.
And if the rule book, the program, is sophisticated enough, your output answers are completely indistinguishable from those of a native Chinese speaker outside the room.
Correct. From the outside, it looks like the room understands Chinese perfectly. You have perfectly simulated the functional appearance of understanding.
But the punchline is?
The punchline, Searle's crucial conclusion, is this. The person inside the room, you, still does not understand a single word of Chinese. You've learned nothing about the meaning. You are just manipulating uninterpreted symbols based on formal rules.
So manipulating symbols isn't the same as understanding meaning. Syntax isn't semantics.
Precisely. And Searle used this to argue against what he called strong AI, the idea that merely implementing the right computer program is sufficient for, or constitutive of, genuine thinking and understanding. He argued computers could achieve weak AI simulating the formal features of mental processes, like current LLMs do, but they wouldn't possess real minds or consciousness just by running a program.
So the computer program, no matter how complex and convincing its output, is just syntax. It's simulating the process of thinking without actually engaging in the meaningful semantic processes required for true understanding or grounding in the world.
That's the argument, yes. Thinking requires that semantic content, that meaning and grounding, which seems to be what's fundamentally lacking in systems operating purely on manipulating patterns in abstract symbols and arrays of numbers.
Okay, so if these AI systems don't actually understand the world in a grounded way, if they don't have intrinsic drives or goals or consciousness, why are so many smart people seemingly so worried about the goal misalignment threat? You know, the nightmare scenarios like the infamous paperclip maximizer thought experiment.
The paperclip maximizer. The AI, given the simple goal of making paperclips that proceeds to convert the entire Earth, and then the universe, into paperclips, destroying humanity in the process because we're made of useful atoms.
Right. That sounds terrifying. If AI gets super intelligent, won't it be unstoppable if its goals aren't perfectly aligned with ours?
Well, that pervasive anxiety, I think, largely stems from a significant overestimation of AI's likely future autonomy and capabilities. And it requires us to accept two highly improbable assumptions about how we would actually design and deploy such powerful machines.
Okay, what's the first improbable assumption?
The first assumption is that a hypothetical, highly intelligent machine would somehow rigidly adhere to our first stated instruction, like maximally paperclips, but then completely ignore all subsequent instructions or attempts at correction, like stop, or wait, that's not what we meant, or let's refine that goal.
That seems like just terrible design, doesn't it? Why would we build something incredibly powerful that we couldn't steer or stop?
It seems like an almost willfully poor design choice on our part. Think about the self-driving car analogy again. Why on earth would we design a car that accepts the first destination you enter, but then immediately locks the doors, disconnects the steering wheel and brakes, ignores the power button, and refuses any further input, so humans absolutely cannot intervene if things go wrong or circumstances change. It defies every basic principle of safety engineering and control systems design.
Okay, that makes sense. What's the second improbable assumption behind the paperclip scenario?
The second assumption is that this machine, which remember likely lacks a truly grounded world model and is utterly dependent on our physical infrastructure for power, data, and manufacturing, could somehow instantly commandeer sufficient global resources and maintain absolute control to prevent humans from simply, well, stopping it. Especially when humans have the clear physical ability to unplug servers, cut power, restrict network access, or just not build the factories it needs.
It assumes a level of immediate, perfect, and physically unopposed execution that seems unrealistic.
It seems extremely unrealistic. Furthermore, there's a strong argument that intelligence itself, understood as the ability to achieve goals efficiently, is actually benign. It's like having a perfect map and a compass.
How so?
The map tells you how to get to any destination, how to achieve any goal you might have. But the map itself has no desires, no drives, no goals of its own. It doesn't want to go anywhere. The goals have to come from somewhere else from us.
Okay, but I have to push back a little here. If intelligence is benign and the goals come from us, isn't the risk then in us specifying the goals imperfectly? If we have to actively design the motivations and if we are the ones programming the AI's objectives, what if we get it wrong? What if we tell it to maximize human happiness and it decides the best way is to hook everyone up to dopamine drips or something equally dystopian that we never intended? The objective itself could be the problem, even if the AI executes it correctly.
That is an absolutely critical point, and you've hit on exactly why the focus of the safety conversation needs to shift fundamentally. It shouldn't be about aligning a potentially rogue superintelligence. It should be about design alignment.
Design alignment, meaning?
Meaning, we must go out of our way from the very beginning to consciously design in motivations and constraints that center explicitly on human values, safety, and crucially, deference to human guidance.
That's the building cooperative AI from the ground up.
Yes. Beneficial machines must be designed, provably if possible, to learn our objectives accurately, to defer to human guidance when it's given, to ask permission before taking significant or irreversible actions, to act cautiously and conservatively when guidance is unclear or ambiguous, and perhaps most importantly, to allow themselves to be easily and reliably switched off or modified by humans without resistance.
So the ability to be switched off needs to be a core, unshakable feature, not an afterthought.
Absolutely. The development of techniques for creating provably beneficial machines, machines designed for deference, corrigibility, and safety, that has to become the core of the new approach to AI governance and development. The real risk isn't that pure intelligence suddenly goes rogue and develops its own inscrutable goals. The risk is that we humans design an incredibly capable prediction and action tool that simply has no built-in incentive to be cooperative, careful, or deferential to our actual nuanced intentions. It's a design challenge, not an uncontrollable emergence.
Wow. This has been an incredibly deep and, I think, clarifying journey through where AI truly excels today and, importantly, where its limits currently lie. We've established pretty clearly that the undeniable successes we're seeing right now in high-precision pattern recognition revolutionizing personalized health, in radically optimized logistics saving industries billions, in instantaneous security prediction, protecting our finances, and in scalable language augmentation, transforming education and communication.
All of those.
They are all fundamentally tasks of cheap prediction and incredibly sophisticated pattern matching. They are powerful tools, but they are not, as yet, signs of human-level, grounded general intelligence.
And grasping that distinction, that current AI is primarily prediction machines, is absolutely essential, I believe, for governing the technology effectively going forward. We need to focus our regulatory efforts, our ethical debates, on the real present impacts of cheap prediction and pattern matching.
Impacts like?
Things like job displacement in specific sectors, the real risks of bias baked into training data perpetuating inequality, the dangers of automated misinformation campaigns at scale, the privacy implications of constant monitoring. Those are the immediate challenges posed by the AI we have.
But as we wrap up, you wanted to leave us with a final thought. As we reflect on this intense focus many people place on the speculative future risks posed by artificial intelligence, your sources suggest we might be, perhaps, focusing on the wrong existential threat, or at least a less immediate one.
Well, it's a provocative thought to consider, definitely. Are we perhaps slightly missing the forest for the trees? shifting our gaze maybe from the theoretical risks of the machine we are building to the known risks of the intelligence we already inhabit.
You mean human intelligence itself?
Precisely. Just consider the historical context of assessing global catastrophic risks. The Bulletin of the Atomic Scientists created the Doomsday Clock way back in 1947.
Right, the symbolic clock counting minutes to midnight, representing existential threat.
For decades now, more than 70 years, that clock has tracked humanity's self-inflicted extinction risks, aiming to highlight just how close we are, through our own actions, to making Earth uninhabitable. It was initially inspired entirely by the existential threat of nuclear war, a product of human ingenuity.
And later they added climate change.
Exactly. In 2007, climate change was explicitly added as another primary driver, pushing the clock closer to midnight. Another consequence, largely, of human industrial activity and decision-making driven by human intelligence.
So these are known quantities, documented threats posed directly by us, by the accumulated consequences of human intelligence, our choices, our tribalism, our short-term thinking.
We are absolutely certain of the potential for great, widespread, catastrophic human suffering caused by human action. We see the impacts of climate change already underway. We know the devastating potential of nuclear conflict. We've experienced global pandemics exacerbated by human ecological choices and responses.
The debate around these issues isn't really about if they are threats anymore, is it? It's mostly about how bad they will be, who will suffer most, and how quickly it's all unfolding.
Exactly. We know these risks are real and present. We struggle mightily to address them effectively through collective human action.
So, given that certainty about the dangers of human intelligence, what is the ultimate provocative closing thought you want to leave the listener with?
Simply this. What steps should we realistically be taking right now to mitigate the proven, immediate, and potentially catastrophic threats posed by human intelligence and its actions, the risks we already know intimately and have struggled to manage for over 70 years, compared to the resources and attention we dedicate to the more speculative potential future threats of artificial intelligence? Is it possible that the real crisis, the one demanding our most urgent, coordinated global attention and action today, is not the intelligent machine we're building, but the often unwise intelligence we already inhabit?